Hi all, Mr. Bruce here. Hey, I just wanted to tell you something really cool happens when you shake an electron. Did you know that if you take an electron and you let it oscillate up and down, you will take the electric field around that electron, and it will also move up and down. So you could imagine if you had a wire that was oriented vertically, you could have electrons in that wire, and if you applied a positive and then a negative, you could move it up, and then if you swap the voltage, you could move it down, up, down, up, down, up, down, up, down. And what happens is when it's up, it creates an upward electric field, and when it's down, it will create a downward electric field. And if you go up and down over and over again, you can get the electric field to oscillate, creating a wave. So I have a simulation here. I'm going to open that up. It's courtesy of FET, and I would encourage you to do the same thing. If I were to take this electron in this metal pole and wiggle it up and down, I create a wave. But guess what that oscillating electric field does to an electron's over on the red house, which is a long distance away? You should notice as that up and down field hits it, it will cause the electrons in that metal rod a long distance away to oscillate as well. Well, if you think about that, that's really, really cool. It's a way that I can get a shaking electrons in one pole to cause electrons in a completely different pole, maybe miles away, to also shake. And you're probably thinking to yourself, gosh, that looks an awful lot like an antenna. And that's exactly the way an antenna works. You have a signal. That signal propagates out. When it hits a receiver, it causes a tiny little wiggle on the receiving antenna. And then that receiving wiggle is interpreted as some sort of sound or ones and zeros, a binary signal, or there are many, many different ways to do that, and we can talk about that in class, but that's how radio transmissions work. So I'm going to go ahead and hit cancel on that. Now, here's the other thing. Those moving electrons, not only do they create moving electric fields, but they also create magnetic fields. If you think about it, if an electron were moving out of the page in this picture, it would create a magnetic field that was counterclockwise. Now, when the electron is moving into the page, the magnetic field is clockwise. And if you think about it, if that wire, instead of being arranged into and out of the page, was arranged vertically, like the wire up here in this blue picture, then you would see an up and down electric field and an into and an out of the page magnetic field. That means that the electric field and the magnetic field that were created by the moving electron are perpendicular to each other. Now, here's the really crazy thing. It turns out that this is a self-propagating scenario. An up and down electric field and a side-to-side magnetic field propagates itself, but it only propagates itself at a certain speed. And it turns out that speed is, wait for it, the speed of light. And what we have created, if you look at the blue and the red, is two sets of fields that are perpendicular to each other that travel in a third direction to the right that's perpendicular to both of those waves. And that is, quite literally, light. That is what light is. It is an electromagnetic wave. And now you know how to figure out the direction of the electric field wobble and the magnetic field wobble because you know the right-hand rule. And these waves are related by this following equation. The electric field strength divided by the magnetic field strength equals C. Or rather, the maximum electric field strength divided by the maximum magnetic field strength equals C. So for example, let's say we had an electric field wave that looks like this. It has a wavelength of 8 meters. It has a maximum displacement of 5 newtons per meter. We could get an equation that represents the graph. All right, that would be 5 cosine of 2 pi over the wavelength times x. And then we could figure out the maximum strength of the magnetic field, or the magnitude of the magnetic field, with E over B equals C, where C is the speed of light. So we've got the magnetic field equals the maximum electric field divided by the speed of light, or 5 over 3 times 10 to the 8th meters per second, which comes out to be 1.67 times 10 to the negative 8th Tesla. So a 5 Newton per meter, Newton per meter, sorry. I just caught myself. It's newtons per coulomb, not newtons per meter. 5 Newton per coulomb electric field equates to a 1.67 times 10 to the negative 8th Tesla magnetic field. All right. The last thing is, it turns out that you can wobble that electron however fast you want. And depending on how fast you wobble the electron, it dictates the color of the light that's transmitted.